Let's start to solve revision questions and start with the problem that says prove by induction that the sum of 2k minus 1 with k going from 1 to capital N equals capital N squared. So that is the first n odd natural numbers add up to n squared for all n in the set of natural numbers. So let's prove this by induction. We'll go through the usual three steps, the first of which is the base case, is establishing the base case, which is check if it's true for some small value of capital N, the smallest possible is n equals 1 in this case. Well, to check this statement, we'll just have to take the first odd natural number 1 and check if it's equal to 1 squared. And that is indeed the case. We have established the base case. Now we can move on to step 2 in the proof. Which is the induction hypothesis. Meaning that we assume that the statement is true for some unspecified number little n. We know that there is already one of these, so it's not an empty assumption, it's not an empty statement. We assume that is true for some little n, meaning that we assume that the sum 1 plus 3 plus 5 plus so on, all the way to little n minus 1 equals little n squared. This is our assumption. Now we can then move on to the last step, step 3, the induction step, where we make the induction step, that is, show that it's true for n plus 1 as well. And the way we have to show this is using step 2, the induction hypothesis. Okay, so for that we need the sum of the first n plus 1 odd natural numbers. This is the first n odd natural numbers from k equals to 1 to 2 to n. But we need the n plus first as well, which is 2n plus 1. We'll do the usual trick, that is to separate this sum into two parts, the first of which contains n terms, hence the induction hypothesis can be applied to it. So this is the crucial point where we apply the induction hypothesis, step 2, to this first piece to say that it is indeed little n squared, that is what we assumed, and the rest of the terms we keep untouched. We'll just carry them forward to n plus 1, and in this expression you hopefully immediately recognize that this is nothing but n plus 1 squared. Which shows that the statement is also true for n plus 1, and in fact the proof is concluded. Now let's move on and consider this complex number z, which is equal to the square root of 2 plus root 2 is its real part. Added to it is I times the imaginary part, which is the square root of 2 minus root 2. We have to compute the square of this number, z squared, and its polar form, the polar form of z squared. And once we have that, we have to use the result to find the polar form of z itself. Okay, so let's start by simply squaring that number. All we have to remember is to square z, square a complex number, or in fact, to multiply two complex numbers, we just have to calculate as usual, with the very important exception that we have I, this imaginary unit, which squares to -1. So as long as we have that in mind, and we apply that, use that, we should have no problem. Okay, so I just copied z over twice, so I'm multiplying it by itself. When I multiply the first terms, I will get the square of this number, which is exactly 2 plus √2. I'm squaring the square root. Then, the next time I will get a real number is when I multiply the terms containing I, because it will give me an I squared, and this is where I should mention that I squared is equal to -1 again. So when I multiply these terms, I squared gives me -1, and the square of this square root will simply give me what's underneath, that is 2 minus √2. Now this is the real part. For the imaginary part, I have to consider the cross terms. So I will get these terms multiplied and these terms multiplied. What it will result in is they look exactly the same, so it's twice I, and then what I have is an expression under the square root. One of them is of the form a plus b, and the other one is exactly a minus b. So remember that a plus b times a minus b is equal to a squared minus b squared. So this is also something I'm using here when I expand this product. And what I will get is a squared, that is 2 squared, minus √2 squared. That is a squared minus b squared in this case. So this whole thing is equal to, well, 2 and -2 cancel each other. Then I have √2 minus -√2. That gives me a plus √2. So I have twice √2. And then what I have here is simply, under square root, I have 4 minus 2. That's taking the root, that gives me √2. So again, what I have here is, for the imaginary part, is twice √2. So the number z squared is equal to twice √2 times 1 plus I. Now I have the algebraic form of z squared. Now let's calculate its polar form. For that, I will need its modulus and its argument. The modulus can be calculated by taking the square root of the squared sum of the real and imaginary parts of this number, but both the real and imaginary parts of this number are twice √2, so I have to square those, add them up, and take the square root. But each of these squares result in 4 times 2, that is 8. 8 plus 8 gives me 16. I have to take the square root of that, that gives me 4. And for the argument of z squared, I have to consider that z squared now is in the first quadrant. Both the real and imaginary part of this number is positive, meaning that if I sketch the complex plane, z squared is in the first quadrant, which means that I can apply the formula giving me the argument of this number, that is applying the arcus tangent function to the ratio of the imaginary and real part of this number. But that is, of course, is equal to 1, because the real and imaginary parts coincide. So that is the arcus tangent of 1, which is pi over 4 radians, or 45 degrees. That shouldn't be surprising, because the real and imaginary parts are the same, which means that this number should be on this line, which has 45 degrees between itself and the real and imaginary axes. Okay, so that is pi over 4 radians, or 45 degrees. Now next, what we need to do now is just to put these things together into the polar form of z squared, which is then the modulus times the cosine of the argument plus I times the sine of the argument. So that's the polar form of z squared. And if you remember the Moivre's theorem, or just simply the formula that we found, gives us the square of a complex number. When it's written in its polar form, we can work our way backwards to get this number in its polar form. What we have to do is simply take the square root of the modulus. So when we square it, we get 4. That has to be 2. And for the argument, we'll have to consider that this number z has positive real and imaginary parts. So not just z squared is in the first quadrant, but z itself is in the first quadrant, meaning that its angle should be between 0 and pi over 2. And indeed, if we take the angle, the argument of z squared, and half it, we get such an angle, and that is in agreement with the Moivre's theorem, or with the formula that we have seen for the square of a number, because squaring a complex number means doubling its angle. So if we double pi over 8, we get pi over 4. We have thus found the polar form of z by applying the Moivre's theorem.